I guess I really should have cranked it out and added it to the last lecture, but I was getting a little tired. So let's pretend that we forgot that we're working on dilutions and just simply read this problem and go from there. You are given a 2.4 molar hydrochloric acid solution. How many milliliters of this solution would be required to prepare 250 milliliters of a 2.5 molar solution of HCl? So this is clearly a dilution where you're given a stock concentration and you are supposed to make up a particular volume of that solution with that solution to make a new lower concentration. So that's definitely dilution. For that we use M1 V1 equals M2 V2. Okay, so the formula says MI VI, whether it's initial or 1 or 2 doesn't matter, and it doesn't actually matter which is initial and which is final as long as you match which two belong together, volume and concentration. For example, if I simply take this 12.4 molar solution and make it M1, that's just fine. 12.4 molar solution. Then I need to realize that V1, which is how much of that solution I need, belongs there. So that is going to be our question mark, or X. And these two clearly belong together because I want, in the end, 250 milliliters of that solution that's 0.25 molar. So that means that M2 is equal to 0.25 M, and V2 is equal to 250 milliliters. And I don't have to change that volume to liters. I can, but since I'm asking for milliliters, you'll see this molarity that's going to cancel, and the volume will be the end unit. So whatever this unit is going to be the answer to your question. Okay, this could actually even be in gallons. It works that way. So we take this formula and solve for V1. So we get V1 equals M2 times V2 over M1. Plug it all in. 0.25 M, I forgot the 2, times 250 milliliters divided by the 12.4 molar stock solution. See what happens to the units here. It's the molarity that cancels, and milliliter comes out in the end. So we have 5.0 milliliters of stock solution required. So that's the answer to our question here. Okay, there is the answer. Let's work another one. What is the molarity of a solution where 25.5 milliliters of a 0.527 molar sodium hydroxide solution is diluted to 500 milliliters? I'm just going to take this first set, V1 here equals 25.5 milliliters. It belongs with the M1, of course. 0.527 M, and that's technically NaOH. And we also know that we want our final volume to be 500 milliliters. And see, this decimal here tells me that I have 3 significant figures. I wanted that accurately. So solving for M2, M2 is going to equal M1 V1 over V2. So we have 0.527 M times 25.5 ml divided by 500 ml. Now here it is important that we have the same unit for the volume, okay? Because that's what's canceling, and that's why it's important that you write those units down. So what I get is, and I'm looking for this problem, it is 0.527 0.00268 m. Okay, here's the answer, set up pretty much the same way I did. Always have your units there so you can see what's cancelled here, right? Milliliters cancels, and molarity is our final unit. Okay, let's take a look at this problem here. It's a little different. Calculate the concentration of each ion present in a solution that results from mixing 50 milliliters of 2.5 molar sodium sulfide and 100 milliliters of 1.5 molar copper sulfate. So now we're mixing, we're not diluting, we're not using a concentration and adding water to it. We are adding an entire different solution to it. And the first thing you have to realize is that these are both aqueous, obviously, or we couldn't have a molarity of it. And what happens when I stick sodium sulfate in solution, I have 2 sodium ions and 1 sulfate ion. Okay, so right off the bat, I don't have a 2.5 molar solution of sodium ions. I actually have a 5 molar solution of sodium ions. Does that make sense, right? Because for every 1 mole of sodium sulfate, I have 2 moles of sodium in solution, right? If I have a single sodium sulfate and I put it in the solution, I will have 1 sulfate ion and 2 sodium ions. So if I'm calculating the concentration of each ion, I'm going to have to take that into consideration. So this gets a little tricky, right? So copper, the same thing. And then you have to realize that both solutions furnish sulfate. So let's do the easiest ones first. The easiest one is copper. So if I wanted to do the concentration of copper ions, so that's Cu plus 2, and putting brackets around this ion indicates concentration. So that indicates its moles per liter or molarity. This I can calculate by taking the milliliters here of the solution times the molarity. Now I am going to show you something here. So we have 100.0 milliliters times 1.50 m, which is moles per liter, right? So let's write this out. Moles per liter of copper sulfate. This gives me the total number of millimoles, right? Yes, you can convert milliliters to liters, but you don't have to. And then liters would cancel. But you have to remember that milli is just a factor of 1/1000th, right? So what cancels here is really just a liter. So my units would be millimoles. And that works great. But if I take this all the way to the end, back to concentration or molarity, now what I need to do in order to calculate, this gives me the number of millimoles, right? I have to divide by the total volume of solution. And the total volume of solution is, of course, both the 50 and the 100 together. So if I divide that by 150 milliliters, I don't even have to worry about millimoles, right? In that case, my milliliter simply cancels. And if this is capital M, then that is just fine. So this will give me an answer of 1.00 m copper, right? That's the concentration of copper. Now, the concentration, I'm going to run out of space here, but I'll fix that in a second. So you can't ask me questions, but hopefully you understand that. Then I'm going to do sodium. I do sodium the same way. I calculate the number of moles of sodium. So we have 2.50 m times 50.0 milliliters. But we have times, there are 2 moles of sodium, Na+, for every 1 mole of Na-. A2SO4. So that is the problem here that you might miss. Still, my total volume is going to be 150 milliliters. Okay, that gives me a concentration of 1.67 m. Now, so I made myself some room. Now we are going to calculate the concentration of sulfate. And so we have sulfate here as a source in both solutions. So we have to simply add up the number of millimoles of that, right? So we have SO4 minus 2, put brackets around it, is going to be equal to 50.0 milliliters times 2.50 m, right? So that gives me, and there's only one sulfate there, that gives me the number of millimoles from source 1. Then it's additive, right? That's going to be millimoles. And then I add that to the 100.0 milliliters times 1.50 m of copper sulfate, also one sulfate per solution, and then simply dividing by 150 milliliters of total solution, and that gives me a molarity of 1.83 m. That would be the molarity of sulfate. Here's the summary of what we just discussed. Again, for sodium you have to have twice as much because there are 2 moles for every 1 mole of sodium sulfate. So that's a dilution. There are a number of other problems that we can work day in and day out. I'm just going to show you one more. Already worked out a titration that we usually do in the lab, but we can't do that in the lab. So here we have an acid-base reaction. If you remember, that's one of those gas evolution reactions. If you have a carbonate and an acid, it's gonna generate carbon dioxide. And so this is a Tums tablet, sodium carbonate. We crunch it up and we add hydrochloric acid in the lab, and we try to determine how much stomach acid this Tums tablet can actually neutralize. So let's read the question here. What volume of 0.15 molar HCl reacts with 75.6 milliliters of 0.375 molar sodium carbonate in the following reaction? So you need to realize that based on this balanced reaction, it takes 2 moles of HCl for every 1 mole of sodium carbonate. And so first you can calculate the number of moles or millimoles of sodium carbonate by simply saying I have 75 milliliters, and I did convert in this case 0.0756 liters times the molarity, capital M, 0.375, so just multiplying those two gives me the number of moles. And now realizing that the stoichiometry, the coefficients, is 2 to 1. For every 2 moles of HCl, I can neutralize 1 mole of sodium carbonate. And then finally, I'm given the fact that I'm using a 0.15 molar solution. And so that conversion factor is, of course, 0.15 moles of HCl. It's here, equals 0.15 moles. I'm sorry, in 1 liter, right? That's just molarity here. 0.15 comes from this conversion factor. Okay, and that gives me 0.378 liters, or 378 milliliters are going to be of stomach acid are going to be neutralized. Well, this is the end. Wow. Good luck on the exam.